Welcome to Conceptual Physics at Delaware Tech, Chapter 28, Reflection and Refraction. So in this unit, we'll talk about what reflection is. We'll talk about the principle of least time. This is Fermat's principle of least time. We'll talk about the law of reflection. And then we'll talk about refraction and the causes of refraction. Refraction is the bending of light when light passes from one substance into another. Then we'll talk about dispersion, which is a special variation of refraction, and this is what happens when we shine light through prisms. We'll talk about rainbows and how rainbows are formed, and it may be more interesting and more complex than you ever suspected. Then we'll talk about internal reflection. And then finally, lenses and lens defects, especially in the human eye. So reflection. We say that light or any type of wave is reflected when it's returned into the medium from which it came. So if light hits something and bounces off, it's returning to the same medium. Say there's a mirror and the light is going through going through air, and it hits the glass and it bounces back into the air. This is called reflection. And we have this little diagram here at the top. This is representing little tuning forks with their own resonant frequencies, just like atoms have electrons with their own resonant frequencies that they prefer to vibrate at. So when light eliminates a material, electrons in the atoms will become more energetic as a result of accepting the photon of light briefly, and that oscillating electromagnetic field that is the photon, that is wave, will come in, hit the particles, be momentarily absorbed and immediately released. And so this readmission will happen. It'll be exactly the same frequency. It'll be exactly the same wavelength and exactly the same speed of light as the original light coming in. Now I say that here, and because this is the simplified explanation of reflection. But I'm going to tell you, if you ever study more advanced physics, you find out that reflection is far more complex, and it's actually considered to be the exact same photon that bounces in and out, and that the pathways are far more complex than we have time to describe in this class. But transparent glass, we know that most of light will go right through transparent glass, but it'll still reflect about 4% of the incident light, of the light that hits it. So if light is going even straight into glass, most of it, 90, 92, 94%, will go right on through. About 2 or 4% will get absorbed because those photons of light will interact with atoms and will be transferred and become heat. And then 4% of it will just bounce right off the glass. So just to think about how much is bouncing off multiple panes of glass, if you have a double pane of glass and that pane will reflect about 4%, maybe absorb about 2 to 4%. If it transmits 92%, in other words, 92% of light goes through the first window in a double pane window, how much will go through 2 panes? Well, it's 92% goes through the first, and then what goes through, it's 92% of the second. If we had a third pane of glass, it's 92% of that. So we would take 0.92, and raise it to the power of how many panes of glass it's going through. So 0.92 times 0.92, or 0.92 squared, would be about 0.85, and therefore about 85% of the light would be transmitted all the way through 2 panes of glass. I'm not going to ask you to calculate the reflection in this case, because you have some reflected and then you have to go through the next glass, and some reflected and then some reflected back. It gets crazy complicated. But if we had mirrors and we had light bouncing from one to another, we could do the same simple calculation of just raising it to the power. All right, so let's introduce the concept of Fermat's principle of least time. You might have heard of Fermat's theorem in mathematics, which was solved about 10 or 15 years ago after not being solved for 300 years. But this is the same Fermat, but he also studied light, and he was studying waves and how they behave. and he came up with a principle that says whenever light or any kind of wave bounces off of something, in other words, reflects off of something, the amount of the pathway it will take is whatever pathway takes the least amount of time. It's always the shortest pathway in terms of time. Now, for reflection, that actually will work out to being the shortest pathway for distance as well. But the rule is the shortest pathway in terms of time, and that will work for both reflection and refraction. The distance part will only work with reflection. We'll come to that later. All right, so it's the shortest path it will take. So if you have some source of light shown at the bottom, like the sun or a star, and you have a person looking at it, that's an eyeball over on the right, and that light will bounce off a surface before coming to the eye. So you have a certain amount of time the light has to take from the light source to whatever it's bouncing off of, whatever it's reflecting off of, and then the time it takes the reflection to reach the eyeball so that you can see it. And that total time, it's the minimum time. Now, what does that mean? It means it will take whatever angle will result in the shortest time getting from the light source to whatever is seeing that light source. And the way we determine these angles is we draw this vertical line perpendicular to whatever surface the reflection is happening on. And we call that vertical line the normal, just like we used normal before to mean a vertical force coming off the surface. Now we mean normal just being a vertical line that comes from whatever reflecting surface we have. So if we want to find the shortest path from a reflection, we make believe that there's no reflection, that it's going straight on through the mirror or the glass or whatever we're talking about. And so if A is the point of the source of light and B is where the light is going to be detected, what you do is you draw a little diagram that has your surface of reflection, and then you draw a line from point A to a made-up point B prime. So where does this B prime come from? Well, you have the real B, the place where, say, your eyeball is at to see the light or whatever is detecting the light, and you make believe that this is a mirror, and you draw where B prime is, the mirror image of point B. So it's actually this imaginary point inside the mirror or inside the reflecting surface. But it has to be exactly the same distance from the surface as the actual point B is, just on the other side. So you draw this point B based on where B is, line it up, draw a straight line through the surface, another normal, and then it will go to the same distance. So you want that same distance that's shown in the dotted green. You want the top distance to be the same as the bottom distance, and you draw on your point B prime. And once you draw that, you draw a straight line from A to your made up point B, your B prime, and wherever it hits the surface, that's where the reflection would happen. In other words, the whole point is to find point C, the point of reflection. And so if you draw that straight line, you'll hit point C wherever it's at the surface. And then now you know that the actual path of the light would be from A to C, and then C to the real point B, not point B prime. And that's how you determine what it is. Well, there are easier ways to do that, and I'll show you, but that's how you think about reflections. And this is the kind of process you're going to use in your problem set. So the law of reflection, we have to define some terms. We already defined the normal. The normal is that line perpendicular to the surface of the reflecting plane's surface. Okay, so if it's tilting, you still have to make it perpendicular. If it's flat, you make it straight up. Whatever the angle of the surface is that it's reflecting off of, you make a line perpendicular to that. That's the normal. Now, you draw a line from your light source to your eyeball, and how do you determine where it is? Well, the way it works is you have the incident light and the reflected light and the normal should all be in the same plane. That's why that little rectangle just appeared on the screen here. They should all be in the same plane. And so when the light comes in, it hits the reflecting surface, bounces to the eye. And the angle of incidence is defined as the angle between the incident light coming in and the normal, not the ground, not the surface, the normal. That might be a little odd. So it's the angle labeled in red here. That's the angle of incidence. And the angle of reflection is the other one. It's the angle between the normal and the reflected ray. So that is fairly easy to do because of what the law of reflection is, which I haven't told you yet. The law of reflection says those two angles are always the same angle. The angle of incidence is always equal to the angle of reflection for reflection, whether it's any kind, no matter what kind of wave it is, sound wave, ocean wave, visible light wave, anything in the electromagnetic spectrum, radio waves to gamma rays. Okay, every type of wave will work. All right, and because these two angles are identical, and that's the only reason this works, because they're identical for reflection and reflection only. Fermat's principle of least time also equates to a principle of least distance. In other words, the shortest path that will make those two angles the same. That's what Fermat's law says. But what it really says is that the time is the shortest as long as you're keeping the two angles the same. Now, I already did one calculation for you with light going through. Here's a calculation if you had a bunch of mirrors. So if you had a single mirror that reflected 95% of the incident light. Well, what if you had a three mirror system, a triple mirror system? So light would hit the first mirror, bounce off, hit the second mirror, bounce off, hit the third mirror, and then bounce off. How much light would be left after three bounces, after three reflections? Well, it's 95% of 95% of 95%. So it's 0.95 raised to the third power, or 0.95 cubed. And that works out to 0.86, which you turn into percent, and it's 86% of the light would make it through all three reflections. So the law of reflection applies to light, sound, both, neither. Well, I just finished telling you, law of reflection works for all types of waves. It's both in this case. While we tend to focus on the electromagnetic spectrum waves, especially visible light in this unit, the law of reflection can apply to any type of waves, any type of rays that come in at an angle, any type of particles that are bouncing, even billiard balls or pool balls in the game of pool hitting a cushion. That angle of incidence off the cushion of the pool table will be the angle of reflection if we had a perfectly non-friction pool table, which we don't exactly, so there's a little variation. So no matter what type of ray or particle or wave is reflecting off of some surface, the angle of incidence will equal the angle of reflection. Okay, so let's consider images that are created from reflections, especially images in a flat mirror, what we call a flat plane mirror. These are your typical mirrors that you would have in your house. And the image that you would see, what we refer to as a virtual image. It's called a virtual image because your eye is telling you that there's an image there, but you couldn't actually put a piece of paper there and have an image projected on it. It's something that your eye and your brain is telling you the light is coming from that direction. There must be an image there. So we have a diagram here with a candle in front of a mirror, and of course the candle is putting out light, but there's all kinds of light anyway bouncing from the candle, all parts of it, towards the mirror. And the light will reflect off the mirror and always have the same angle of incidence as it does the angle of reflection. So you get these equal angle reflections off of the mirror, now, no matter which direction the light hits the mirror. But if you trace back the reflecting light, so the arrows that are coming off of the mirror, and you trace back where your brain tells you the light is coming from, in other words, straight line back into this imaginary world within the mirror, you would see an image there that's not really there. It's an image that your brain would tell you is formed there, and that's your virtual image. and that virtual image will be exactly the same size as the object that is in the mirror, and it could be you in the mirror. Whatever it is, it will be the same height, the same width, all of the same dimensions. In addition, the image of the object will be the same distance behind the mirror, imaginarily behind the mirror, as the actual object is in front of the mirror. In other words, if it's 1 meter in front of the mirror, the image will appear to be 1 meter into the mirror, behind the mirror. And what that also means is no matter where the object is, its distance to the mirror, whatever that distance is, it's double the distance would be from the object to the actual image that you see. So the image distance to the object is always twice the actual distance from the object to the mirror. It's always twice as wide. So if you were to walk into it towards the mirror, your image would be coming in to you as well, and everybody would be walking so that whatever speed you were walking in the mirror, it would appear like the image is approaching you at twice that speed because the image is moving into you at the same speed you are. All right, so let's do this same analysis with a person standing in front of a mirror. So the height of the image is going to be the same as the height of the person. The whole dimensions of the image will be the same as the actual real person in front of the mirror. And when a person is looking in the mirror, the light from the top of their head is going to bounce into the mirror, and some of that light will bounce back to their eye, and the angle of it hitting there will be the same angle as it reflected back to you. That's the law of reflection. The angle of incidence equals the angle of reflection, and I've shown it a little dotted line to represent the normal, so you can see the two angles are the same. And the light that came from the bottom of your shoes might also hit your eyes, and that will have the same incidence angle as it does reflection angle. So you have these two lines of light, the two red lines, that are the lines that reach your eye from the bottom of your body and from the top of your body. But your brain doesn't know that light bounced off the mirror to reach your eye. It doesn't know that light may have curved before or bounced off. It has no idea. Whatever direction light is coming at you, your brain says that's the direction light must have come from. So your brain does this little calculation and says, oh, it must have come from back there behind the mirror. And as a result, you see this image that's not really there, that you see, that you think is behind the mirror, when obviously that can't be true. And that is the virtual image, an upright virtual image. In other words, it's not upside down. It's the same orientation as you are. It's from bottom to top. And so it's an upright image, but it's a virtual image, not a real image. I couldn't put a piece of paper back there behind the mirror and have the image projected on it. Nothing would happen if I did that. You wouldn't see it at all. But what's interesting here is if you look at the mirror itself, you realize that only a small portion of the mirror is actually necessary to generate this virtual image that's supposedly behind the mirror. So if this man standing in front of the mirror was 6 foot tall, he would see an image of himself 6 foot tall. If he was standing 6 feet in front of the mirror, the image would be 6 feet behind the mirror to his eyes looking at the image. But what's interesting is the part of the mirror that's actually used for his reflection is only half of his own height. It's only 3 feet. Only 3 feet of the mirror is used, and that's because he's the same distance away, so you have these similar triangles. It's what's called in geometry. If you made a triangle between the mirror image and the two full red lines, you see this big triangle pointing to your left. But if you start at the mirror with the short purple line and the solid red lines, you have the same triangle, but just the shorter version of it. It's half the length of the original triangle, half the width of the original triangle, and therefore all of its dimensions are half, including the part that's in the mirror compared to his mirror image. And therefore this part here that's actually on the mirror is always half of the mirror image height, which is the same height as the real person. So you only need half the mirror to see the full height of any individual. And you might think, well, wait, what if I stand back or get close? If you stand back from the mirror, the same thing happens. So you have this same guy standing further from the mirror. The image will be as well just as further back from the mirror in that imaginary virtual space. But if you look at the new lines of reflection from the top of his head and from the bottom of his head, and you trace back to the new image of his body back behind the mirror, you see that the part in the mirror is still exactly half of the height. Nothing changed. So it doesn't matter how far you are from the mirror, how close you are from the mirror. You only need half your height to see your full height in the mirror. If you're 5 foot tall, you only need a 2.5 foot mirror to see all of yourself, no matter how far away you're standing from it. All right, so let's talk about what's actually being reversed in a mirror. We have a woman standing in front of a mirror, brushing her hair, and if you were to ask somebody what is reversed, most people will say, oh, it's left and right are reversed in a mirror. But you have to understand, left and right is a relative term. It's relative to whoever is speaking. So the person, the real person, would say left is here and right is here, and this imaginary virtual person in the mirror would say the other way around. They would say that right was over this way and their left was over this way if they're facing the person looking into the mirror. So that's really a relative term to the speaker, but it's not an actual direction. So if we were to actually introduce coordinate system here, so you see there's an X and Y axis in the diagram on the bottom, the mirror diagram on the bottom. And if we put a Y axis in and we say, okay, Y, we'll call Y the direction forward. I'm sorry, Z is the direction forward, Y is the direction up, and X is the direction this way, to this side, okay? Well, if you look at the mirror image, the X and Y directions are the same. Y is still pointing up, X is still pointing over here. I'm not going to say right, it's pointing over here. But Z is now pointing forward instead of back. So the Z direction is the only inverted direction in the mirror. So that would be the front to back inversion. It would be the front to back axis that's actually inverted in a mirror. Not really the left to right, because left to right is not really an axis. It's this direction is positive and this direction is negative, and that'll be the same for both you and your virtual image in the mirror. And if we were to take the whole thing and turn it sideways and make a lake a mirror or a pond a mirror, you're looking into it. Remember, the direction that the lake would reflect is top to bottom, up and down. So what was up would be down into the lake in that case. That's just because we're rotating the whole mirror sideways. But the images will appear in a different plane. So if you're standing here, the image will appear in a plane behind the mirror that is parallel to the real person. That's parallel to what is reality. All right. So the image is virtual, meaning it's not real. In other words, your brain is telling you that there's an image back there, but you couldn't actually put a piece of paper behind the mirror and capture that image. Because there's nothing behind the mirror for real, you're seeing it within the mirror only because the light that's bouncing back to your eyes, you assume came from a straight line that leads to inside the mirror as a virtual image. All right, so we talked about these plane mirrors, the flat mirrors, but what about with curved mirrors? You can have what's called a convex mirror. That's a mirror that curves outward. So the edges go away from you and the center is closer to you. And that would be the picture on the left with the gentleman looking into the convex mirror. His virtual image is still upright. The bottom is still the bottom, the top is still the top, but now it's smaller. And it's smaller because if you follow the lines of the arrows that reach his eyes, the two arrows that reach his eyes, his brain will tell him that an image is coming back behind those arrows from straight lines, and that will plot out a smaller head than what he actually has. So he'll see a smaller image of himself. But if you have a concave mirror, so this is a mirror that curves outwards, so the center is further from you and the edges are a little closer, you're going to get the opposite effect. You'll still get the light bouncing into the mirror and to your eyes, either from the bottom of your head to your eyes or the top of your head to your eyes. But now if you trace back the lines that reach the eyes, you trace them back imaginarily into the mirror, you end up widening to get an image that's much bigger than the actual person's head. So concave mirrors will give bigger images, a virtual image that's upright and larger and also further away. Whereas the convex mirror on the left will give a virtual image, so it's still upright, it's still a fake image, but it's smaller and it'll be closer to the person actually looking in the mirror. And there are the traced lines back so you can see what they're actually thinking they're seeing. All right, so light reflecting from a smooth surface undergoes a change in frequency, speed, wavelength, neither A nor B. Now, we didn't cover all of this, but I'm going to tell you that reflecting light is exactly like the light that hit the surface. When it bounces off, it comes back to your eyes. Your book describes this as similar to the transmission of light through glass, where an atom will pick it up real quick, it'll absorb that photon momentarily, and then immediately spit it out. If you start studying more advanced physics, you find that the photon is never gulped. It's literally just reflected, but in a very complex way. But the point is, whatever light comes off looks exactly like the light that was incident to whatever the surface was it hit. So it'll be the same frequency, it'll be the same wavelength, and frequency times wavelength is speed of the light, so that will be the same as well. So nothing changes for reflected light. And it'll have the same frequency. If it has the same frequency, it also has the same period. It'll have the same wavelength, and it has the same speed. So during reflection, we're going to say that the electrons capture the light momentarily and basically re-emit it, but it virtually identical photons that are released, so there's no difference between any of the characteristics. All right, so let's talk about diffuse reflection. This is reflection off of a bumpy surface, off of a rough surface with quote-unquote irregular surface features. And in this case, remember, the law of reflection still works. The problem is we don't have a flat surface to draw this beautiful vertical normal line, so we know, oh, this came in at this angle, it must bounce back at exactly the same angle. The incident angle and the reflection angle are identical still, but the problem is the surface is changing angles wherever the light hits it. So if the light hits it in one place, the surface might be flat and your normal's here, but over here you might have a little bump, and now the normal is a different direction, and maybe the surface is over like this, and now the normal is this way. It's always perpendicular, and the angle of incidence will always be the same as the angle of reflection relative to that normal line, but the normal line is changing everywhere along this bumpy surface. So you get these real weird reflections all over the place that almost appear like scattering of light. But there really are reflections, it's just the reflections are different for every point along the surface. And so you can get an undesirable circumstance with a ghost image in TV when TV signals, these are the actual radio signals that might bounce off of buildings or other obstructions. Radio signals that might be traveling, hundreds or thousands of miles to reach your TV, they have very long wavelengths. But buildings are big, and they can interfere with these wavelengths of electromagnetic spectrum, so that you won't get everything coming into your TV the way it should, and you'll get these odd images on your TV on occasion. So if we have a bumpy or slanted or curved surfaces, the normal is always perpendicular to the surface, but that's going to change everywhere on a bumpy surface. And as a result, we'll get our reflecting rays all be different depending on where on this bumpy surface it's hitting. So in order to cause dispersion, the irregularities might be larger. They must be larger than the wavelength of incident EM wave. What does that mean? That means the waves of light, whatever wavelength we're talking about, radio waves, which are huge, or visible light, which is considerably smaller, or ultraviolet light, which is even smaller wavelengths because they're higher frequency, smaller wavelengths. And then gamma rays have really small wavelengths. Whatever they're bouncing off of, if they fit inside these bumps, if they're smaller than the bumps, they're going to be affected by this dispersion of waves all over the place. And but if they're bigger than the pits and the bumps and the roughness of the surface, they won't notice it. They'll just bounce and bounce off. So irregularities that are smaller than the wavelength, that's said to be polished for that particular wave. In other words, it's flat enough to not affect it. If we're talking about big wavelength EM waves like radio waves can be meters or even hundreds or thousands of meters. They're gigantic waves with radio waves, and if they can't fit in a bumpy surface, they don't see the bumpy surface, and they just bounce off as if it was a smooth, polished surface. So if you're asking whether something is polished for a certain wavelength of light, you have to look at how big the wavelength is and how big the bumps are, how big the surfaces are, how big the obstructions are in whatever it's hitting. And if the bumps and grooves are big enough for the waves to fit into, they're going to be affected by this diffuse reflection. If they're not big enough to fit into, they'll see it as if this perfectly smooth surface and just bounce off, and we call that polished. All right, so different road surfaces will determine how much of this diffuse reflected light actually reaches our eyes. And the big difference here is between dry surfaces and wet surfaces. On a dry road surface, which has a certain amount of roughness to it, there's going to be diffuse reflection on different parts of the road, but the light that hits the road, some of it will hit your eyes and you'll be able to see the road perfectly well. And that's why we can see the road reasonably well when we're using our car lights. Even though we hit it with the light, some of it will bounce back to our eyes because of these weird angles of hitting the road, and we'll be able to see the road perfectly well. But if the road is wet, now the road, yes, becomes smoother because there's water on it, but more importantly, the light will come in and there's less diffuse reflection because it's smoother. And so if we've got headlights, most of that light is not going to be bouncing back at us because of these weird bumps and features on the road. Most of it will just come in at the angle our car lights are pointing at the road and bounce back away from us, so we won't see that much. So there's not much light there. Plus, some of the light will be caught inside the water and bounce around and reflect there, and some of it will be absorbed, and just less light will come to our eyes. And as a result, the surfaces will just look darker to us as well. All right, so diffuse reflection occurs when the sizes of the surface irregularities are A, small compared to the wavelength of reflected radiation, B, large compared to the wavelength of reflected radiation, C, both, D, none of the above. Well, remember, the reflections will only be spread into all these different directions if there are grooves and bumps and irregularities that are big enough for the waves to fit into. If they're not big enough for the waves to fit into, the wave just sees a totally flat surface and there's no diffusion at all. It just comes in with a nice clean reflection. So if the surface irregularities have to be bigger than the wavelength so they can fit into the waves can fit into the little grooves on the ground or the bumps on the ground and be affected by it. So it has to be, the surface irregularities have to be larger than the wavelength, big enough for them to fit into these pits and grooves to be affected. So waves of the electromagnetic spectrum, no matter what type of light we're talking about, anywhere from radio waves to gamma rays, they have to be smaller than the pits and grooves in the surfaces for them to even notice it. Larger wavelengths like radio waves and microwaves that can be very big, they're too large to fit into the little bumps and grooves in a road, so they just see a totally smooth surface and just bounce off cleanly. All right, so let's talk about a totally different topic here, refraction. We've been talking about reflection, where light comes in at an angle of incidence, and you have the normal, and then it bounces off with the same exact angle for the angle of reflection. In other words, the angle of incidence exactly equals the angle of reflection. But there's another kind of movement of light if the light can go into the second medium. If it's going from one medium to another, there might be some reflection, but you might also have some of the light going into whatever it is. If you're going from air to water, or from water to air, or air to glass, or glass to air, any of those is a change in medium, so the light can go through it, but it doesn't go through it straight, depending on the angle that it hits that surface between the two substances, what we call the difference between the two medium, the air medium and the water medium, for instance. And that is called refraction. And now we have a new definition to introduce. We still have the angle of incidence. It's still the angle relative to the normal, to the perpendicular. But instead of having a reflection off the same surface, some of that light, or most of that light, will go into the water in this case, and it will bend at that point. And we measure, instead of the angle of reflection, the angle of refraction, which is still the angle that the light is traveling between it and the normal line. So the normal, we have to draw the normal into the surface, into the second medium, and look at the angle here. So we have that angle of refraction. And these are rarely going to be the same angle. They really are not the same angle. But Fermat's principle still works. It works exactly well. It says that whatever path it takes, it's going to take the path that will take the least amount of time. But with refraction, you can't say it's also the least distance. Distance doesn't work with refraction. Fermat's principle of least time still holds up perfectly well, but you can't use distance. Now, what does this mean? Well, here's a perfect analogy, and I've used this before, and it's funny because this was one of the first questions I was ever asked to solve in a college calculus course. If you have somebody on land, on the sand, a lifeguard, and they're at point A, and you've got some person in the water at point B, they're not directly in front of them in the water. They're down the coast a little bit, but in the water. The quickest route for the lifeguard is not to do a straight line right to the person that's in the water, because swimming in water takes a lot longer than running. You want to increase your running time so that you can decrease your water time. And the best way to do that is to spend more of your time in the sand, in this case running, than you are spending your time in the water. And light does the same thing with air and water. Light would take the long path through the air and the short path through the water, because light goes much faster in air than it does in water. And so it's whatever will achieve the least time from one point to another if it's going through two different media. So you would take the dash line in this case. You would take a path that's not a direct line from A to B. You would take a path where you're spending more time in the sand running than you are you're more distance in the sand running than you do the distance you're spending in the water swimming. So light does exactly the same thing. So if you have light going from point A eventually to point B, and both of those are in air, but you have a sheet of glass in between, it has to get through the glass. So it's coming in from A to the glass. And the quickest way would be this dashed line here. But that's not the way light would travel. It's not going to go straight through the glass without bending and going to C, because light is faster through air than it is through glass. The average speed, I should say, not the speed of light between particles. The average speed in air is faster than the average speed in glass, and we'll talk more about that later. So light travels slower on average in the glass than it does on air. So it tries to cut back on the time it's spending in the glass and increase the time it's spending and distance it's spending in the air in order to get through with a total time that is the quickest time from point A to point C in this diagram. So when light exits a glass, the average speed of the light and wavelength will kick right back up to what it was before when it was in air. So as long as it's in air, when it comes out of the air, it's still exactly the same speed and wavelength. Those are the same. And the frequency is always the same no matter what it's doing, but the frequency changes, the wavelength and speed change in the glass relative to the air. The frequency never changes. It's the same light going through it all the way, but it will slow down through the glass, and that means the wavelength will also get smaller as a result. So light rays, if we have light passing from air into water, and we have a little mirror at the bottom of the water, so it bends when it hits the water, and then it reflected from the mirror and then has to come back out into the air. And you'll notice if we draw a normal line where the light is going from air to water, and we draw another normal line where the light is coming back out from the water to the air, we have these two vertical lines. And if we can compare the angle of incidence, the first angle of incidence, this is between that first light beam from the flashlight and that normal that's there on the left. That's our first angle of incidence. And then we have the angle of refraction. And you'll notice going to water, the angle of refraction is smaller than the angle of incidence in the air. And then when it comes out, it reverses that pathway. So now the angle from the water to the air, we call that first angle the angle of incidence. So this is from the mirror going out of the water. That's the new angle of incidence. And we have the new angle of refraction when it's going from water to air on the far right. But so what we see is if we're going from something less dense to more dense, the angle of refraction is smaller than the angle of incidence. If we're going to something that's less dense like air, the angle of refraction is bigger than the angle of incidence. We'll talk more about why that is here. All right, so this is really related to the speed of light, and that's the main driving force why we have refraction. So if we want to measure the effect of substances on the speed of light, we use something called the index of refraction. We abbreviate it just N. Index of refraction is sometimes known as the refractive index. It means the same thing. And it's the ratio of the speed of light in a vacuum, so that's the fastest light's going to be usually, to the average speed in the material. So we literally take the full speed of light in vacuum, about 300 million meters per second, and we divide that by the speed, the average speed in glass or in water or in air or in diamond, whatever it is we're talking about, which is going to be slower. So it's going to be a bigger number divided by a slower number. So the speed of light in a vacuum is almost always faster than the average speed of light through any matter. I have a little asterisk here. There are some very special circumstances way beyond the scope of this course where that might not be true, but for your purposes, we're always going to assume that the speed of light in a vacuum is the fastest version of the speed of light. And as a result, the refractive index is always going to be greater than 1, because the speed of light in a vacuum is always going to be faster than the number we're dividing it by, the average speed of light in water or air or diamond or glass or whatever we're talking about. So the index of refraction really tells us how much light is going to be bent because it's changing speed as it's going through a new material. The denser the material, meaning the optically denser, in other words, slowing down light, the denser the material, the slower the average speed of light. If we slow down the average speed of light, we'll have a higher refractive index. In other words, it's a bigger difference between this new speed and the original speed in a vacuum. All right. So slow speed means high refractive index. That means light will bend more towards the normal. So if you're coming in obliquely, that means at an angle here, and you've got refraction. Here's our normal. The angle it's going to make in the denser material will always be smaller. In other words, it'll be bent. It'll instead of keeping it the same angle, it'll tilt towards the normal and make it a smaller angle in denser material. So whenever we're going to denser material, the angle will become smaller. because the light will tend to bend towards the normal. So here it is written out in kind of a quick form. If the optical density, in other words, how tightly packed the particles are that affect light, is higher, the average speed of light will go down, the refractive index goes up, which means refraction goes up, which means the bending of light goes up, and that also means that the wavelength will go down. Now, frequency doesn't change. Because we're not changing frequency, the speed of light, the average speed of light, is proportional to the wavelength. Remember, speed equals frequency times wavelength. So speed is proportional to wavelength. If the speed is going down and we're not touching frequency, the wavelength is also going down. So the frequency will always stay the same with refraction. It also stays the same with reflection. Everything stays the same with reflection, but with refraction, the only thing that stays the same is frequency and period, because period is just calculated 1 over frequency. All right, so here it is in mathematical form what the refractive index is. It's the speed of light in a vacuum, that 300 million meters per second, divided by the average speed of light in whatever substance we're interested in the refractive index of, or the index of refraction, same thing. So a medium with a high refractive index means it's really dense. It means the speed of light is slowed down on average, and it means there's a lot of bending towards the normal. It's going to, instead of going whatever direction it was, it's going to tilt closer to perpendicular, the perpendicular line, the normal line. So we know the index of refraction for glass and diamond, etc. We know the index of refraction is really high for diamond. That's greater than glass. Glass is greater than water. Water is greater than the index of refraction for air. And then vacuum, it's just 1, because it's the speed of light in a vacuum divided by the speed of light in a vacuum. So N in a vacuum is just 1. And this mirrors the opposite direction for the speed of light. The speed of light, C, in a diamond is slower than the speed of light in glass, and that's slower than the speed of light in water. It's slower than the speed of light in air, and the speed of light in air is just a little tiny bit slower than the speed of light in a vacuum. So these are going to always be in the opposite direction. In fact, if you have the fraction of the speed of light, like for diamond 0.41, it's just 1 over 0.41, which will give you the N. All right. So it turns out that objects with the same refractive index as whatever liquid we stick them in, if they're clear objects, we can't see those objects because there's nothing to bend the light, and light just goes through them. We don't even notice there's an object in there. And magicians actually use this. They'll take objects that you can see when they're not in the water, and they might be clear enough, like a glass rod or something, and they can actually hide them in, say, a container of oil, that clear oil that might have the same refractive index as the glass, and you drop this in, it's completely invisible to the human eye, so people think something disappeared, or they don't notice there are things in the liquid helping the magician with the trick, because if they have the same refractive index and they're both clear, you won't notice the one inside the other. Another use of refractive index, a more practical use of refractive index, is materials with high refractive index can bend light more. So they make lenses from materials that have a higher refractive index, like glass and certain plastics. And this is why the glasses that we use, I mean, they have glass that will bend light in order to focus light to help people with vision problems. And that is because lenses can refract the light. Anything can refract the light, and if you carve the lenses in the right shape, they will refract the light just the right way to focus light into a point and make clear images for anybody using them. All right, refracted light that bends towards the normal is light that has A, slowed down, B, sped up, C, nearly been absorbed, D, diffracted. All right, remember, bending towards the normal is what you get when you're going into a denser substance where light has slowed down. The reason why you're bending towards the normal, it's more perpendicular to where the light's traveling through. And in other words, it's a shorter path. The light will bend to make a shorter path when the light is traveling slower on average. and that will be when the substance is making the light slow down. So we have a little diagram here of light coming from, say, air into water or into glass. It's going to slow down when it gets into the water or the glass. We'll go water for now. So when light passes through a denser material, as soon as it hits the denser material, it slows down. The average speed goes down, the wavelength goes down, the frequency stays exactly the same. But because it's slowing down, it picks a path that's more direct through the material, which tends to be closer to the normal, bending more perpendicular. And that's because of the principle of least time. It will take that more direct path because it's going slower as it's going through this material. So a slower light will bend towards the normal, trying to make a shorter path for itself. And this is the analogy that you have to rescue someone in the ocean far down the beach. You maximize how much time you want to spend flying through the air quickly or running on the beach quickly, so that you don't spend as much time with your light going through the water or you swimming through the water, because that takes more time. That's slower. So you pick the path that will take the least time for you to get to the drowning swimmer, or for the light to get through the water. So it'll go at one angle through the air, and when it gets to the water, it takes a steeper path through, which is closer to the normal, in order to minimize the time it's spending in the water. All right, so refracted light that bends away from the normal, this is just the opposite question, is light that has slowed down, sped up, nearly been absorbed, diffracted. So if it's bending away from the normal, it's basically light that's able to spend more time in that new medium. Well, that's a medium that the light can travel faster in, so that's sped up. So this is the opposite situation. We're going from light in the water to light in the air, or light from glass into the air. And now you might come in at a certain angle of incidence. The incident ray comes in, and then it will take a shallower angle coming out. It doesn't have to be as steep, because it can spend more of distance in the area where it can move faster, the air in this case. So light passes through the less dense material, it speeds up. And the principle of least time tells us it'll spend more time traveling in the place where it can travel fast, the less dense material. So faster light, when the light gets faster, it'll bend away from the normal, making it less perpendicular to the surface. And again, the analogy is you're in the ocean this time, and you need to get way down the beach on land, on shore. So you don't want to spend most of your time swimming to the shore swimming the whole length and then just walking to the last few feet on the shore. You want to spend a little time swimming, just enough to get you out of the water and maybe a little bit of an angle, and then you can run the rest of the way on the sand, which will be a lot easier. And it's the same thing here. All right, so refraction. Refraction causes a lot of things that we see in everyday life. And one of them is illusions that we see about where we think light is coming from. You've all seen somebody stick a straw in a glass of water and the straw looks bent. This is refraction. You can see it from the side. You'll see the straw appears to be bent. If we're in a swimming pool, it'll look like our legs are shorter in the swimming pool, and that's because of the light bent from the light that's coming from your legs through the water to your eyes that are up here in the air. So objects that are submerged, objects underwater, the light from them will appear as if the object is higher up, less, not as deep in the water. Okay, well, why is that? Well, let's look at a fish underwater here and somebody looking at the water, looking at the fish. So you have the fish's true location deep in the water. So the light is going to come from the fish up to the surface of the water. It's going to come up in all directions, but the direction that will eventually hit your eye comes up at a certain angle. And so you see the light coming up, and as it hits the air, it'll get to a more shallow angle, it'll go further from the normal. In other words, the angle of refraction in this case will be bigger than the angle of incidence under the water. And so the light bends because it's now moving faster. It'll take the longer path when it's moving faster, it'll reach your eye. But here's the weird part. Remember, the eye doesn't know the light has bent. The eye and the brain tell the person that the light is coming from the same direction that the light that hit the eye was. So we see these rays, number 3 here, we see these rays coming in that direction, and we just assume they came from that direction the whole way. So our brain assumes this path that's labeled number 4 here, that's where we think the light must have come from. And as a result, our brain tells us that the fish is in a different position, a position that's higher up, closer to the surface of the water, between the water and the air. So our brain tells us it's in one position that's higher than its true position. So objects will appear to us along a straight line, leading us to see that object at point 5 on this diagram, because we think everything came from a straight line along that line that's labeled number 4, not really coming from where the true fish is. Coming from where the fish truly is. There are a lot of different illusions that happen that are due to refraction. One of them is the sun. When the sun is setting, we tend to see different versions of the sun as it's setting, and that is because even if the sun has set below the horizon, the air itself will reflect the light because there are changes in temperature, there are changes in thickness of the air. The light from the sun is going through empty space before it hits the air, and as a result, even if the sun is below the horizon, we'll still see the sun. We'll see the sun as being higher up than it actually is, and this will make the sun either look like it's above the horizon after the sun is set. It'll even make the sun look a little longer, make it look oblong in the sky, a little higher, long and thin instead of circular when it's at sunset. So refraction is actually responsible for a lot of different things. The sun looking elliptical, this oval shape of the sun, having that extra daylight even after the sun is set, because some of the light is refracted and we see the sun higher than it actually is. But you also get mirages. These are the mirages in the desert or when the surface of the ground is super hot, and we'll talk more about that in the next slide. We've already mentioned how when you're in a pool or any objects in a pool, it looks up higher than it actually is because of the refraction of light and where we think it's coming from. So that makes our legs look short and stubby in a pool when we're in the water. The twinkling of stars at night, this is due to refraction as well. We see a star because stars are so far away, not like the planets that are much within our solar system. Stars are much, 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 much further away. So essentially, by the time they reach us, they're just a pinpoint of light in the sky, but they don't look like a pinpoint of light in the sky. We see them sparkling. Well, the reason why they're sparkling is that light from that pinpoint source many light years away is eventually traveling through the Earth's atmosphere. And there are different parts of the atmosphere that have different temperatures. And as it's traveling through these different pockets at different temperatures, it's refracted because cooler air is a little denser. It slows the average light speed down. Warmer air is a little less dense. It lets light go a little bit faster. And as a result, going through the different parts of the air, it's refracted in different ways before it hits our eyes. And this is constantly changing in the atmosphere. So we see this twinkle because the light is refracted. It's constantly changing as we're looking at it. So we don't see that nice clean pinpoint of light for each star. We see this light moving around so it looks like it's twinkling to us. And then the last example here, diamond sparkling, the sparkling colors of a diamond. This is because diamonds are cut purposely in order to get light refracted into them at such an angle that some of the light is actually trapped in there and starts reflecting inside the diamond before it's finally refracted out towards our eyes. And because there's so many internal reflections, which we'll also talk about soon, these internal reflections, by the time it reaches our eye, there are so many of them, we see light coming from many places within the diamond, and so it appears to be sparkling with all these beautiful colors. All right, so mirages. Mirages happen because we have differences in temperature between the air that's right above the ground and the air that's higher up. And remember, the hot air down below is less dense, so light will go a little faster. the cooler air above is denser, so light will go a little slower. So if you have some object in a distance, and the light is going to come from that object in all directions. But some of that light might be coming down towards the ground, towards the hot air, and the hot air is where the light will speed up, and it will start bending towards the cool air, which might be you standing up tall, and you would see the light bending toward you. So the hot, less dense air near the ground is where the light is slightly faster. The cooler, denser air up higher is where the light's slightly slower, and the light tends to bend into the cooler, denser air where it's slower. It's going to bend towards what would be the normal, which I haven't drawn here, but it would bend towards the air where it moves slower, and some of that light will hit your eye. But remember, as people with eyes and brains, we think the light is coming from a straight line. So we would see whatever image, if this was a palm tree in a distance, it would appear to us as if there was some upside down palm tree under the sand. If we're looking at a distance, we would see this image inverted and somewhere in the sand itself if we were looking on a hot desert. But you can imagine that if this was not a tree here, and we were just getting light that was coming from the sky, and the sky, some of the light was coming down to the ground, and some of that was bent up towards our eye because of this refraction in the air of moving up to the cooler air from the hot air that's close to the ground. If we saw, instead of a palm tree, we saw the sky that was underneath the sand, we wouldn't think, oh, that's sky on the ground. That's blue sky. We would think, oh, that's blue water. And this is why people in the desert will see images of pools of water on the sand up ahead. It's really just the sky, the image of the sky, that light coming down to the ground and refracting back up to our eyes, and our eyes just assume it's coming from a straight line that happens to be below the sand, and we think we see blue pools of water on the sand, when in fact we're just seeing the blue sky that has been refracted. So when light travels from one medium to another and changes speed in doing so, we call that process reflection, interference, dispersion, refraction. Well, we've been talking about this. This is refraction. So what are these others? Well, let's talk about refraction first. It's the light passing from one medium into another, air to glass, hot air to cold air, water to glass, water to air, whatever we're talking about, where the molecules quickly absorb the light and they emit it at the same frequency. So it's going through, it's being captured and released, captured and released, but it's the same frequency, but now we change the speed because it's going through either a denser material where the speed will decrease or a less dense material where the speed will increase. The speed and the wavelength move together. They're proportional to one another. So if the speed goes down, the wavelength gets smaller. The speed goes up, the wavelength will get bigger. Now reflection, we've already talked about that as well. This is when the light is momentarily captured and immediately released, and you get what looks to be exactly the same light in the process. So you get a light with the same frequency, the same wavelength, the same speed, the same period, and then bouncing off, it looks exactly the same. No difference between those. Interference, we've talked about this. Interference is when you have more than one waveform and you're just adding and subtracting them together, so it doesn't really relate to this directly. Dispersion, we haven't really talked about. Dispersion is a special case of refraction caused by prisms. This is when light of white light, so white light contains all the different colors of the rainbow, it hits the prism, which is typically made of glass or plastic. It's going to refract at the surface between the air and the prism, but different wavelengths of light will diffract differently, and we'll talk about that in a minute. All right, so the cause of refraction is all based on the changing of the speed of light, the average speed of light, when you're going from one medium into another. So if you were, the left diagram here is you're pushing a cart or you're driving a lawnmower or whatever, and you're going from the sidewalk onto the grass is going to be slower. So you take the more direct path on the grass. You take the less direct path on the sidewalk because you can move faster on the sidewalk than you can on the glass. Well, the same thing with light. Light going through the air, and it hits water, it will take a more direct path straight through the water, so it'll be closer to the normal, closer to perpendicular to get through that water, a shorter path, so the angle of refraction will be smaller than the angle of incidence in this case. And that's all due to this speed of light. And if you look at the wavelengths here, you can see the waves, the wave fronts hitting from air into water. When they hit the water, the wavelengths, the distance between these waves gets shorter, but the same amount of waves have to get through. So the frequency stays the same, the wavelengths get shorter, and the whole speed gets slower as it's going through the more optically dense material, the water in this case. So it's caused by a change in average speed of light going through the material. When the frequency is the same in refraction and reflection, it's the same when you're going to a new medium, but in refraction, the wavelength and the average speed do change. If you're going to a more dense material, both the wavelength and the average speed will go down. The frequency stays the same. All right, so dispersion. Dispersion is a special case of refraction, but refraction affects different wavelengths differently, different frequencies differently. High frequencies are more affected by refraction than low frequencies. The higher the frequency, the more it will bend than the lower frequencies will bend. So blue light and violet light, they have a higher frequency than red light and orange light. So the blue and violet light will bend more when you're coming out of a piece of glass in a prism. Remember, you always have to look at it relative to the normals, and the normals are all at these weird angles because the prism is triangular shape. So I've got these dotted lines that represent the various normals here. And if you look at white light, remember that's the mix of all the colors coming in. It hits, if you look at the angle that the white light is coming in relative to the normal, there's a wide angle there. It's narrower for red, but it's even narrower still for blue. Blue is even closer to the normal than the red is in that first refraction here on the left. But by the time you get to the other side of the prism here, the red and blue have already been separated. When they exit the glass or the plastic, whatever the prism's made out of, they bend. There's even more bending here. The blue will bend more as it's coming in the air, bending away from the normal more than the red will bend away from the normal. And so you'll get an even greater separation of the red from the blue and the violet. And then all the other colors of the rainbow are somewhere in between. So it looks something like this. You have that white light, that mix that comes into one side, and the first refraction will bend the red light a little bit, the orange light a little more, the yellow light a little more. But by the time you're at the blue, indigo, violet, you've got more bending. And then when it exits, that effect is even more amplified with the bending. The red will bend a little bit, but the violet will bend much more. The violet and the blue will bend much more. And you can get this with prisms. You can also get this with a very high-tech piece of equipment called a diffraction grating. This is a specialized piece of equipment that has essentially little bumps in it, little ridges. I'm not going to go into detail on it, but these will also separate frequencies of light with refraction on them. So the higher frequency of light, like blue and violet, refracts more than the lower frequencies of light. And this is because in glass or in water or whatever they're refracting in, blue and violet light are slowed down more than red and orange light are. So you get more bending of those wavelengths of light. The higher the frequency, the more it will refract because there's a bigger effect on its speed, the average speed of light of that, whether it's going through glass or water, whatever. Okay. I have the little mnemonic on the side so you can remember the order of the rainbow. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. We usually don't even mention indigo. A lot of people are dropping it from the official colors of the rainbow, by the way. All right, when white light passes through a prism, green light is bent more than A, blue light, light, B, violet light, C, red light, none of the above. Well, green light's in the middle, right? We have the low frequency red light. We have the high frequencies blue and violet light. I just finished telling you that the high frequencies are refracted more than the low frequencies. So red's the least, blue and violet are the most, green is in the middle. So green light will bend more than red light. It'll bend less than blue and less than violet. So in the vacuum, all EM waves travel at C, at the vacuum speed of light, 300 million meters per second. But in non-vacuum media, in other words, anything that's not pure vacuum, higher frequencies will travel slightly slower than the lower frequency material, so they will be refracted more. Higher frequency will go slightly slower and therefore will be more refracted. So as a result, high frequencies of light will bend more, low frequencies of light will bend less. In the visible light, in order of the Roy G. Biv, you got the reds, the least refracted, the violet and blues, the most refracted, and then yellow and green are right in the middle. They're in the intermediate refracted. They're all refracted. So red has the lowest frequency within the visible range, green is higher, and the blue, and so as a result, green will be more refracted than red. That's a long way to say that. All right. So rainbows. Rainbows are also a phenomena caused by dispersion, by refraction, by multiple refractions of different colors of light. But now instead of a prism, each raindrop in the sky, especially after the rain has stopped and there's a lot of raindrops just floating around in the air, each one of those raindrops can refract light. And in fact, they will refract light twice, once going into the drop and then once coming out of the drop with a little internal reflection before that. So you have refraction of the light going into the drop. It's inside. There's an internal reflection in the drop. And then when the light exits the drop, you get another refraction further separating the colors. So the bottom diagram shows you how the colors start widening and how they separate in the raindrop. So each raindrop is producing its own little rainbow. However, you only get to see one single frequency from that raindrop because only each of the different wavelengths of light, each of the different frequencies of light exiting the raindrop, a single raindrop, are coming out at different angles. So depending on where you're standing, you're only going to see one of those rays hit your eyes. So you'll only see one color from each raindrop. So in this, what you notice in this diagram, looking at the red description here, for both refractions, the violet light is refracted more than the red light. Remember, violet light is higher frequency than the red. So it will have, by the time it exits, it's coming out at a tighter angle than the red light is. So the violet light in any one raindrop is kind of pointing up, and the red light is slightly down from that by a couple degrees. And so you'll see different wavelengths depending on where you're standing relative to that raindrop. So if you have a number of raindrops, some of the raindrops will give one raindrop up here will give you one frequency of light, a raindrop down here will give you a different frequency of light. And oddly enough, I just showed you how the raindrop has the violet light bent more up and then the red light bent more down. You might think, oh, I'm going to see the red light on the bottom and the violet light on the top, but that's not exactly what happens. What happens is, since each drop is only sending one wavelength that reaches your eye, the raindrop that's showing you the red has to be lower, has to be a higher drop because its angle is down steeper. So when you see the violet light, that must be coming from a lower drop in order to reach up to you. And as a result, we see the rainbows with the red on the top and the violet on the bottom. So each drop will produce its own spectrum of colors. Only one frequency will actually hit our eye from each drop, depending on how high up it is in the sky. But you need millions of drops with all these different frequencies of light for all the different colors of the rainbow for us to actually perceive the rainbow. Now, we just talked about it as if this is column of raindrops producing light that makes the rainbow. But we know the rainbow is a bow shape. It's a big arch in the sky, a big arc in the sky, arch in the sky, however you want to call it. But that is our perception of it, depending on where we're standing. The reality is we're looking at this giant three-dimensional cone in the sky. And we don't see the bottom of this cone because there's ground there. We just don't see the bottom half of it. But what we're looking at, when we're looking at a rainbow, we're seeing a rainbow, and right behind that rainbow is a taller rainbow, and right behind that's a taller rainbow, and right behind that's a taller rainbow. So the angle we're looking at it, it looks like one rainbow to our field of vision from our angle. We see the collection of all these individual bows shown in red here, and whatever bows are formed within the drop region. The drop region is just basically the width of the air that has a lot of water in it, where you'll even get this dispersion pattern, where you get these refractions from the raindrops. And so when they add up, you're looking at essentially millions of rainbows, one behind the other, stacked behind the other. But because they're all in the angle you're looking, it appears like one rainbow to you. But you're actually looking at this giant half cone of rainbow. It just looks like a single bow to you from your standpoint. The bottom one you don't see because it's under the ground, but people have been in airplanes, and you've probably seen these YouTube videos and or TikTok videos where somebody's flying in a plane and they see the whole rainbow is actually a giant circle. It's actually an entire cone, depending on where you are looking, but you're looking from the center of the cone, so you think you see what looks like a circle, but it's actually a circle that's getting bigger and bigger as it goes away from you, and you see it as a circle, but it's really a giant cone that has a certain thickness to it. You just can't see that thickness from your standpoint. So all the drops disperse the rainbow's light to you will lie in the shape of the cone. So you're getting one wavelength of light from these raindrops up here, and then slightly lower you'll get a different frequency of light, and slightly lower you get a different frequency of light, and you get the highest frequencies below, and you get the lowest frequencies at the top, and that's why the rainbow looks red at the top and violet at the bottom. So you have the red, the orange, the yellow, green, blue, indigo, violet in that order. So the cone has these thicknesses of layers in it, and you just don't see that thickness of layers. You're looking as if you're looking in this bottom diagram. It's like you're looking along a straight line, and you see this arc that's really just a projection, a squeezed together version of that cone you're really looking at. So the thicker the rain area is, the drop area is, the more versions of the rainbow you're going to see stacked behind one another, and therefore the more vivid the colors will be of the rainbow. So if you see a rainbow that's barely visible, there's probably not a very thick area of water out there in the air. If you see a really intense rainbow, it probably goes back really far. That cone probably extends quite a distance, and you're looking through the thickness of that cone. So in the bottom diagram here, you're looking only, you see that arc, but the arc is really a chunk of cone that you don't see the thickness of. So it's really a bunch of semicircles. If you're in a plane, it's a bunch of circles that get bigger and bigger as they go behind one another. But that's the way you view it, as a rainbow, a single rainbow, but it's really not. All right, so rainbow facts. We've already shown that in a raindrop, you have a refraction of the light going in, you have an internal reflection, and then you have a refraction as the light is coming out. So it's two refractions and one reflection. Every drop acts like a prism and makes a whole rainbow, but you only get one color, one frequency from every drop because it's spread out, so only one frequency happens to be the right angle to hit your eye. If you moved into a different place, you'd get different drops that would give you those frequencies, but you'd still see a rainbow, but it would just be from different drops matching different frequencies. So your rainbow is always going to be slightly different than everybody else's rainbow. Technically, you're seeing different sets of drops making different colors than the person standing next to you. They're at a different angle, so their red wavelengths would come from slightly different drops than your red wavelengths, your red frequencies. And as a result, the rainbow moves with you. Depending on your angle, you're going to see different drops are going to be reflecting just the right light to your eye at any one point in space. And the bow is going to be brighter. The rainbow is going to be brighter depending on how thick that water drop region is in order to get those multiple layers of refractions, one behind the other. We've also heard about other rainbows, the quote-unquote double rainbow that there's some very famous videos about. And the double rainbow, the second rainbow, is always going to be fainter. And the reason why it's fainter, I don't have a diagram for this, but the reason why it's fainter is instead of having one refraction of the light going into the drop and then an internal reflection and then the light coming out of the drop, instead you get the light refracting into the drop, and then there are two reflections in the drop. So it bounces around a couple times before it refracts out of the drop. Well, coming out, as a result, you have that extra reflection as well as the two refractions. So more light has to do different things, and every time light reflects or refracts, a little bit of light is captured, a little bit of light is lost due to absorbance. So if you have more reflections, some of that light won't reflect and some of it will be just lost and will not ever reach your eye. As a result, the second rainbow just looks fainter than the first. The other thing about the second rainbow is the colors are in reverse direction. So instead of having red at the top and violet on the bottom of your rainbow, it's the opposite. It's violet on the top and red on the bottom. And the reason is that second reflection inside the raindrop points the light up. It literally crisscrosses where the light comes in, so everything is inverted in the process by this extra bouncing inside the drop, and now the new rainbow has the reverse direction of the colors. All right, compare with the primary rainbow. The secondary bow is A, dimmer, B, has colors reversed, C, is caused by two internal reflections, D, all of the above. Well, I just finished telling you it's dimmer because of the extra reflection and the extra absorbance from during that reflection. And because that extra reflection has an angle that's pointing up higher, you end up reversing the order of the frequencies of light and reversing the order of the colors. So it's all of the above. We get that second reflection inside the raindrop. The second reflection causes the final refraction with the exiting of the drop basically pointing at a higher angle, so it's up higher in the sky, and that higher angle actually also reverses the directions of the colors, and the extra reflection is accompanied by extra absorption, so less light hits our eyes and the whole bow is dimmer. All right, so we're going to stop here and we'll do the second part in the next video.